We got protons, neutrons, and electrons. Okay, so we've got those basic components of molecules, or of atoms. And it's those base components that we associate certain things with. Okay, so protons. You might have heard these described differently, but this is the way I like to look at it. The interior of our atom, we have a nucleus. And in that nucleus, we have protons and neutrons. And on the outside of the nucleus, we have electrons. Well, I like to think of the protons as what defines the element. Okay? It's not perfect, but it gets pretty close. The neutrons define the isotope, or the mass of our element. That's, again, not perfect because protons also have a mass, and they contribute to the mass. But if I'm defining it as just the mass of the element for our neutrons, if I change the element, what happened to the protons? The element changes, what happens to the protons? They also have to change. Okay? So it's looking at what they most directly imply to. And then the last one, our electrons really define our charge. Okay? Well, really our charge is defined as the balance of positive and negative things. Okay? So protons contribute to that. But if I change the protons, am I changing just the charge? No, I'm changing the element. Okay? So those kind of subcategories allow us to define these. Okay? And another thing that's going to become more and more important as we look at these is, why do we have neutrons? Okay? 'Cause when we initially discovered atomic particles, we had electrons first, which then led us to the decision that we had to have protons. Because if we have electrons that are negatively charged, but we have atoms that aren't charged, there has to be something to balance out that negative charge. Okay? So that's why we have protons and electrons. Why on earth do we have neutrons? Be careful, right idea. Stability of what? Buffers the protons from each other. Well, we can understand a positive and a negative. They're attracted to each other. They neutralize. Okay? Everything we do in organic chemistry strives to one thing: neutralize. You take a sodium ion. What is it most commonly found next to? Chloride ion. Why? Chloride's negative, sodium's positive. Why are they so attracted to each other? Because they're trying to neutralize charge. So charge is something that is inherently high energy and dangerous. Right? Can we see that in our everyday life? We've got these little gray boxes floating around the room. Okay, how many of you had an older or younger sibling that told you to stick a fork in them? Okay, you all had very nice siblings. Okay, really bad idea to do that, because what happens? You get shocked. You get a massive electrocution coming out of that. Well, what's coming out of the wall? Electrons, charge. Charge is inherently a high energy state. Everything we do in organic chemistry is to neutralize that charge as best we can. And we'll neutralize that through varying aspects. Okay, we can pair it up with different atoms, okay, or different solutions or solvents. It's a question of finding a balance between those situations. Okay, so neutrons come into play because where are all our protons? All together in the nucleus, which means we took one positive charge that we already know is unstable. That's why we put electrons near it. Okay, and we put that positive charge near another positive charge. What happened to our charge? Did it get higher or more neutral? Became more charged. Well, what was charge? High energy and bad. So to even have a nucleus, we have to have something neutralize that charge. Hence, our neutrons. Our neutrons are merely trying to allow that charge to be dispersed appropriately to stabilize it and allow it to exist. Okay? So the principles that we're running organic chemistry off of go all the way back to these subatomic particles. We're trying to neutralize that charge as best we can. So we can now move to the electrons. Okay? And that's it with nuclei, okay? Which brings up an interesting question. We spend 152 talking about radiation and all sorts of other fun stuff like that. We go, oh, that's cool. Nuclear power, yay, whoopee. Organic chemistry, I don't care about the nucleus anymore. The only thing I care about are the electrons. Okay, why? Organic chemistry is the study of carbon interacting with anything. Well, if I take a carbon atom and interact it with any other atom, what's the first thing that interacts between those two atoms?
The valence shell.
The valence shell, or even less specifically, the electrons. So what I'm concerned about are the electrons interacting with each other. And if I have some understanding of where my electrons exist, I can start to predict their interactions. Right? So we've got a rough approximate energy shell distance all the way up here. So we'd start to place our electrons into these energy shells. And this is where we got our atomic line spectra. Right? And as we added electrons in, we could then account for all of our structures. Well, we move up to probably about n equals 7, maybe 8, as far as energy levels go, before the gap between the energy level and the vacuum, meaning the electron's not attached to the atom anymore, becomes so small that the atom almost instantly flies off into the vacuum. Right? Why has that become a problem? How many electrons can fit in an orbital? In a single orbital, we can only get 2 electrons. Well, if I only have 8 energy levels, 2 electrons, 8 orbitals, I get 16 elements. How many elements? A lot more than 16. Right? So something else was going on, and that's where we saw divisions within those energy levels, and we saw different orbital types coming out of that. Okay? We can now place more electrons in. We still didn't account for our proper number of electrons. So we end up finding that our orbital types can categorize even further. Okay? And we end up with all these different sections on the periodic table, which in theory you've heard referenced as potentially the what block? S block, because the outer electrons for any element within those first two columns are in the S-type orbitals. The next section is the P. Next section, you're going to tell me the P block. Or P block is over here. Okay? Why do we see more columns come out of this? There's more orbital types that come out of this, so we can fit more electrons into it. And then we've got the D block with our D orbitals. So as we get further away from the nucleus, we can start adding in these different suborbitals and these subcategories that come out of them. Okay? So we could then look at pictures of these. Okay? And going back and forth on how much we want to look at these pictures. Okay? But if we take a look at our energy level 2, we have the S-type orbital and the P-type orbital. We get these shapes. Everybody should be familiar, hopefully, with the circle and the dumbbell shape. But why are they a circle and dumbbell shape? What does that circle mean? If I take a single electron and I'm going to put it into a 2s orbital. So here's my single electron, my symbol for an electron, just that little dot. Where would I draw that dot? Is that correct? Is that correct?
No.
Yes, it is correct. What does the circle represent?
The electron.
It's the 95% probability, which means the electron can exist in a lot of different spaces around that. At just 95% of the time, it exists in this tiny little sphere. Right? When we look at the dumbbell shape, that's what's happening there as well. So our electron is constantly moving around, but its highest likelihood of being found is within that space. When we move to the p orbitals, it's found within those space. Why do we end up with 3 orbitals when we move to the p orbital, where s only has 1? Good look at the number of columns. That's kind of cheating. We got a bunch of extra columns when we move to the p block, which means we have to have more orbitals. Why are there 3 different orbitals? It has to do with the orientation. It comes back to the mathematical theory about how an electron can move. When we look at the s orbital, there is only one orientation. If I take a sphere and I turn that sphere, and then I tell you to close your eyes, okay, thanks for listening, and I turn it again, could you tell that I necessarily turned the sphere? No, there is only one orientation for a sphere. What happens with a dumbbell shape? If I turn that, can you tell it was turned? Yes. those different orientations are now at slightly different geometric shapes, which then means we get different places that we can locate the electrons. Okay? And it just so happens that when we solve mathematically for the p-type orbital, that there's 3 possible orientations. What happens when we move to the d-type orbital? We get 5 different orientations. Okay? One of the things that makes things awesome about organic chemistry, how many orientations do you need to worry about? Just the S and the P. Those are the only 2. We don't worry about the D. Why not? Because it's confusing enough as it is with just the S and P. No, actually, that's where all of our chemistry typically happens, is within those S and P, within organic chemistry. Because organic chemistry was based on what element?
Carbon.
Carbon. What are the orbitals available to carbon? S and P. Okay? Yes, that is time. So I will go ahead and stop. Feel free to go ahead and